Alright, what's up guys? In this video, I'm going to pick up some calculus here, and this is going to be another integration practice video, more specifically a trigonometric integration practice video. So we're asked to evaluate this definite integral here from 0 to the power over 2. We got sine to the 7th of x dx. So a couple things I wanted to mention very quickly about the trig integrals. So what makes trig integration hard is the fact that a lot of students don't have their trigonometric identities memorized. That creates a bit of a problem, because the techniques that we use to evaluate trig integrals really aren't that different than the integration techniques that we apply to evaluate integrals that don't contain trig functions. You know, you still got your use substitution, your biparts, your partial fractions, stuff like that. It's just that in most cases with these trig integrals, you're going to be given some trig function that you don't immediately know an antiderivative for in most cases. And as you can see in this case, we got sine to the 7th of x dx. So you got to ask yourself, do I know an immediate antiderivative for that? No. And on top of it, it's a definite integral. So it's just a nightmare, right? So that's what makes it difficult. So if I could give you one word of advice when it comes to trig integration, you need to memorize your trig functions. Otherwise you will not like, or memorize your trig identities. Otherwise you will hate trig integration and trig substitution. Now, for some of these trig integrals of trig functions that are of higher order, not in this particular case, but in some cases you can use what are called reduction formulas. And these are just some of them for the trig functions. These are very useful when you have trig functions of higher order. They obviously are very helpful. The problem is you can see that each of these formulas are quite long. And so it's a little bit of a challenge to memorize them. And I don't know too many professors out there that allow you to use trig identity sheets or even reduction formula sheets, at least not in the calculus classes that I've taken. When I was getting my degree, we had to memorize all of our trig functions. So the reduction formulas are helpful, but they can't be used every time, and they're quite difficult to remember. So what you have to do for a lot of these trig integrals is break the expression up. Now, if it's not raised to a higher power or something like that, there's no big deal. But you need to break it up a little bit, and that's essentially what we're going to have to do with sine to the 7th. So let's break it up a little bit, and we'll use some trigonometric identities for it. So sine to the 7th of x. So you want to start by breaking this up. So sine to the 7th of x, remember that's just sine to the 6th of x multiplied by sine of x, because although it's not explicitly written, this sine here is being raised to the first power, and if we have the same base, we add the powers, thus giving us 7. So that's the same thing. However, this doesn't really make it any easier, so we need to break it up a little bit. The good news is that 6 is an even number. So for sine to the 6th of x, I can break that up and simply write that as sine squared of x cubed. Because we know what we do, we take the powers and we multiply them. Another good thing about sine in this particular case, if we remember our trig identities, remember that sine squared of x, that's just going to be 1 minus cosine squared of x. Because remember your Pythagorean identity that sine squared of theta plus cosine squared theta, or just theta, is equal to 1, not of theta, but just theta. And if I wanted to solve that for sine, well, again, I would just basically subtract cosine squared theta from both sides. So now what we're going to do is we're going to transform this integral. Now, when you're breaking the integral, or you're breaking up the trig function, you know, to kind of rewrite it, I'm going to leave the limits of integrate. I didn't do anything that would change the limits. All I did was rewrite the function. So that's a common mistake as well. I need to change the limits. No, we didn't do anything. All we did was break up the function. So now I'm going to rewrite the function. So I still got my sine there. And then this time, I'm going to rewrite this as 1 minus cosine squared of x. And this time, it's going to be cubed, and we're going to evaluate it with respect to x. Okay. All I did was just break up that trig function. And now it's something that we can integrate, because we can do a use substitution now. And that's how most of these trig integrals are. You got to break them up. Reduction formulas are helpful, but they're quite long, and they can't be used all the time. So in this particular case, we certainly want to pick u to be cosine, because its derivative is out here, and we know how to cancel it out. So we'll pick u to be cosine of x will then differentiate it to get negative sine of x. So the derivative of our u is not exactly the same technically as what's out here, because there's a difference between positive sine and negative sine. But if it's if you can end up canceling out something, then it's fine. So it doesn't have to be exactly the same, but you need to be able to cancel something out. So I'm just going to move the negative to the side. So then we're going to have negative 1 over sine of x. Du is equal to dx if we solve for the dx part. And essentially what's going to happen is the sine is going to cancel out, because the sine here is in the denominator. We have a sine up here, and it would just essentially cancel it out. Now we're going to have to change the limits because we did a u substitution for a definite integral. So I'm going to leave the bounds blank, and that just leaves us with a negative on the outside. And then it looks like we'll have 1 minus u squared cubed du. Okay. All right. So the next step is to go ahead and expand out a lot of this stuff. So let's just expand out some of this here. That's the best thing to do. You can change the limits first if you want to, or you can change it after. It doesn't make a difference when you do it, as long as you do it. So, well, matter of fact, why don't we go ahead and do it now? I guess it's not a big issue. So we got cosine of x was our u. So all we got to do is stick in a 0. So we get cosine of 0, when we know that's 1. And then we get cosine of pi over 2. Cosine of pi over 2 is 0. So that does create a little bit of a problem, because we would have 1 is the would have 1 as our lower limit and 0 as our upper limit. And your upper limit of integration, it doesn't matter which is smaller or bigger, but in cases like that, what you can do is you can flip the limits and change the sign of the integral. That's pretty much all you have to do in cases like that. So I'll tackle those on after we do and I'll change the sign of the integral and all that stuff after we do the expanding. So let's just deal with the 1 minus u squared cubed. Okay. All right, well, that's just going to be 1 minus, looks like I'm going to get 3u cubed plus, I'm going to get 3u to the 4th power. And we know that 2 times 3 is 6, so this would be minus u to the 6th power. Now, we got the negative that's on the outside there, and we can go ahead and distribute that in to take care of the issues with that. Okay. All right, so if we distribute that in, we simply get negative 1 plus 3u squared minus 3u to the 4th power plus u to the 6th power. All right, so we've expanded it out. I'm going to keep the negative on the outside because we flipped the limits of integration, and since we flipped the limits, we have to change the sign of the integral. And then the integral just becomes the integral from 0 to 1. We got negative 1 plus 3u squared minus 3u to the 4th power plus u to the 6th power. And then we're integrating all that with respect to u. Okay, so as you can see here, just through the process of breaking the integral up, we've made it a little easier. Let me get another sheet. Again, I'll do a video, maybe, I don't know, maybe I'll try to do one tomorrow where we use show you how to use those trigonometric reduction formulas in certain situations. That can certainly be helpful. So we'll just continue here. And hopefully you guys can see. Let me turn my camera light back on. All right, so you can basically just go through and apply the sum and difference rule for integrals and kind of break it up on your own. Just set it there so I can see it. So I'm just going to do it step by step. So let's just deal with each of those. So from 0 to 1, we'll integrate negative 1 du. Well, evaluated from 0 to 1, that's just going to be negative 1. And then from 0 to 1, we'll integrate 3u squared du, and that's going to give us 1. We're going to integrate from 0 to 1. Now you would apply the, again, the sum and difference rule and actually write it out in a certain way. I'm not doing that here. I'm just kind of breaking it up and doing it step by step so you can see what's going on. So this is not technically written the correct way, but you get my point. So in this case, again, so we got our three to constants. It's to be u to the 5th over 5 from 0 to 1. So we know this become 3 over 5. And then the last one was from 0 to 1, u to the 6th power du. Well, that obviously gives me 1 over 7, because it would be u to the 7th over 7 from 0 to 1 would give us 1 over 7. And so now what we have is we have our negative on the outside, and we stick in. So we got negative 1 plus 1 minus 3 over 5 plus 1 over 7. So we just got our negative out there, and this is negative 3 over 5 plus 1 over 7. So we go ahead and get our calculator. 16, I think it's gonna be 16 over something, but let me check. Remember, to add and subtract fractions, you need common denominators. So sometimes, depending on what the fractions are, I can get the answer off the top of my head, but that involves finding LCM. Yeah, so, well, I was partially correct. I said positive 16 over 35, but it's actually negative 16 over 35, but it will change to a positive because we got a negative on the outside. And so in this case, if we deal with that, this would be positive 16 over 35, which will actually be the answer. So your final answer for this definite integral, this trig integral here, will be 16 over 35. So from 0 to pi over 2, we were asked to integrate sine to the 7th of x dx. And our answer to this is 16 over 35. Also, make sure that you're taking your calculator and checking your arithmetic. If you're not completely sure that you got it right, then you need to be plugging it in, making sure that it's correct. And that is your answer. So just another trig integral. I already have several on YouTube, so this isn't the only one that you have to look at, but it's just another general idea. All right, so I will see y'all next time.